Download this code from codegive.com, link in the description below. OK, let's dive into dynamic CMOS logic design, covering the fundamental principles, VLSI considerations, advantages, disadvantages, and a basic code example. This tutorial will be quite detailed, aimed at a VLSI design level of understanding. Dynamic CMOS logic, a deep dive. 1. Introduction. Dynamic CMOS logic is a design style that offers potential advantages in speed and area over static CMOS logic, but at the cost of increased complexity and potential issues with charge sharing and noise. It relies on the temporary storage of charge on the capacitance of a gate to represent logic levels. Unlike static CMOS, which provides a path to either VDD or GND in steady state, dynamic CMOS gates have a precharge phase and an evaluation phase. 2. Core principles. Precharge phase a clock signal, CLK or phi, controls the operation. When the clock is low, the output node, often labeled out, is precharged high through a pmos transistor. This sets the output to a known state. Evaluation phase when the clock is high, the pmos precharged transistor turns off, and an NMOS transistor network connected to GND is evaluated. If the input conditions to this NMOS network are met, it creates a path to ground, discharging the output node. If the inputs do not enable the NMOS network, the output remains charged at a high voltage, thanks to the capacitive load. 3. Basic structure. A basic dynamic CMOS gate consists of the following components. PMOS precharged transistor This transistor is connected between VDD and the output node. Its gate is controlled by the clock signal, inverted or not, depending on the design. When the clock is low, typically 0V, this transistor turns on, charging the output node to VDD. NMOS evaluation network This network, also called the evaluation logic, is a set of NMOS transistors configured to implement the desired Boolean function. This network connects the output node to GND. NMOS clock transistor This transistor, often called the foot transistor, connects the NMOS logic network to GND. It is also controlled by the clock signal, often the same as the pmos, but sometimes the inverse in other more complex design styles. When the clock is high, typically VDD, this transistor turns on, enabling the evaluation network to discharge the output node if the inputs allow it. Some dynamic logic styles omit this foot transistor, but it helps reduce leakage and contention. 4. Operation timeline. 1 clock low, precharge. PMOS transistor turns on, the output node is precharged to VDD. NMOS transistor turns off, the evaluation network is isolated from GND. The output node's voltage is determined primarily by parasitic and load capacitances. 2 clock high, evaluation. PMOS transistor turns off, the precharge path is disabled. NMOS transistor turns on, the evaluation network is enabled. If the input conditions to the NMOS network are met, i.e., the inputs cause a conductive path to GND, the output node is discharged to GND. If the input conditions are not met, the output node remains at VDD, precharged value. 5. Advantages of dynamic CMOS logic. Higher speed dynamic logic can be faster than static CMOS due to smaller input capacitance, fewer transistors are connected to the output node. No contention, during evaluation, there's no direct path from VDD to GND. Asterisk full swing output, the output voltage swings from VDD to GND, providing higher noise margins for subsequent stages. Asterisk smaller area asterisk requires fewer transistors per gate compared to complementary static CMOS. A complex function can be implemented with a single NMOS transistor network. Asterisk lower power consumption asterisk with fewer transistors and less contention, dynamic CMOS can consume less power than static CMOS in some applications. 6. Disadvantages and challenges. Asterisk clocking requirements asterisk dynamic logic requires a clock signal, which can introduce complexity in clock distribution and timing analysis. Asterisk charge sharing asterisk a major concern. If the output node has to be discharged but not directly to GND, instead, it can share the charge with the internal nodes of the NMOS evaluation network, which can cause the output voltage to drop incorrectly. This is especially critical when the output is supposed to remain high. This is often mitigated by precharging all internal nodes of the evaluation logic to VDD during precharge. Asterisk clock feed through asterisk the clock signal can capacitively couple to the output node, causing noise and potentially affecting the logic level. Asterisk leakage asterisk even when the NMOS network is supposed to be off, small leakage currents can slowly discharge the output node. Asterisk noise sensitivity asterisk because the output node is floating during the evaluation phase, it is more susceptible to noise. Asterisk non-robustness asterisk dynamic circuits require careful timing analysis and design to ensure correct operation. Asterisk monotonicity asterisk dynamic logic only allows for monotonic evaluation. This means that once the output starts to discharge, it cannot be charged back up during the same clock cycle. This characteristic introduces challenges in realizing complex functions directly. However, this can be overcome by using cascaded designs, but those designs are susceptible to other issues. Asterisk cascading issues asterisk directly cascading dynamic gates, the output of one dynamic gate driving the input of another dynamic gate, is problematic because the input of the second gate might start evaluating before the first gate's output is valid. This can lead to incorrect evaluation. This is known as the charge redistribution problem. Solutions include using static inverters between stages or more advanced domino logic, described later. 7. Charge sharing, a detailed explanation. Charge sharing occurs when the output node is precharged to VDD during the precharge phase, and one or more internal nodes in the NMOS evaluation network are initially at 0V. During the evaluation phase, if the input signals activate the NMOS network, the charge stored on the output capacitance, COUD, can redistribute to the internal capacitances, SINT, of the NMOS network. This redistribution can cause the output voltage to drop below the threshold voltage of the next stage, leading to incorrect operation. Mitigation techniques for charge sharing asterisk. Asterisk precharge internal nodes asterisk the most common solution is to precharge all internal nodes of the NMOS evaluation network to VDD during the precharge phase. This ensures that there is no charge redistribution when the evaluation phase begins. This is typically implemented by adding pmos transistors that are switched by the inverse of the clock signal. Asterisk increasing output capacitance asterisk increasing the size of the output capacitor reduces the percentage change in voltage when charge is shared, but this can decrease the circuit speed. Asterisk transistor sizing asterisk carefully sizing the transistors in the NMOS network can minimize charge sharing by reducing the internal node capacitances relative to the output capacitance. 8. Clock feed-through, explanation. Clock feed-through is the unwanted coupling of the clock signal to the output node. This is due to the parasitic capacitances between the clock line and the output node. During the clock transition, the coupled charge can cause a voltage spike on the output node, which can potentially lead to incorrect operation. Mitigation techniques for clock feed through asterisk. Minimize parasitic capacitances. Careful layout techniques can minimize the parasitic capacitances between the clock line and the output node. Clock buffering. Using clock buffers can reduce the slew rate of the clock signal, thereby reducing the amount of charge coupled to the output node. Dummy capacitance. Adding a dummy capacitance to the output node can help to absorb the charge coupled from the clock signal. 9. Domino logic, a popular variant. Domino logic is a specific type of dynamic logic that addresses the cascading issue and the monotonicity requirement. It does this by adding a static CMOS inverter at the output of the dynamic gate. This inverter is sized to drive the load, which allows for more complex functions to be implemented. How domino logic works. 1. The dynamic gate's output is precharged high during the precharge phase. 2. The static inverter inverts this output, so the domino gate's final output is low. 3. During the evaluation phase, if the NMOS network evaluates to true, the dynamic gate's output is discharged low. 4. The static inverter then switches, causing the domino gate's final output to go high. Benefits of domino logic. Easier cascading. Domino gates can be easily cascaded because the output is always in a known state, low, during the precharge phase, and it only makes a single transition during the evaluation phase, low to high. This ensures that downstream gates don't start evaluating prematurely. Higher speed. Generally faster than static CMOS for complex gates. Area efficiency. Can be more area efficient for complex functions. Drawbacks of domino logic. Inverting logic. Domino logic is inherently inverting. Non-inverting functions require additional inverters, which can increase area and delay. Clock load. The clock signal is heavily loaded, requiring larger clock drivers. Noise sensitivity. Still susceptible to noise. Power consumption. Higher power consumption than static CMOS due to the switching activity of the inverter. 10. Example, dynamic CMOS and gate. Let's look at a simple example, a 2-input dynamic AND gate. This gate will output a 1 only if both inputs A and B are 1. Explanation of the Verilog code. Inputs CLK, A, and B are the clock, and the 2 input signals respectively. Output. Out is the output signal, declared as a reg because it's assigned a value inside an always block. Always at, CLK or A or B. This sensitivity list means the always block executes whenever there is a change on CLK, A or B. If, CLK, this condition checks if the clock is low, precharge phase. Out equals 1B1, sets the output to high, VDD, during precharge. Internal _ node equals 1B1, this precharges the internal node, which is important for avoiding charge sharing issues. Else this block executes when the clock is high, evaluation phase. If A and B, if both A and B are 1, the output will discharge to 0. Out equals 1B0, discharges the output to low, G and D. Internal _ node equals 1B0, discharges the internal node to G and D. Else, if A or B, or both, are 0, the output remains high. Out equals 1B1, output maintains its precharged value, VDD. Important considerations for implementation. Simulation thoroughly simulate the design to verify its functionality and identify potential charge sharing or timing issues. Layout careful layout is crucial to minimize parasitic capacitances and ensure signal integrity. Timing analysis accurate timing analysis is necessary to guarantee correct operation under various process, voltage, and temperature (PVT) conditions. Clock skew minimize clock skew to ensure that all dynamic gates in the circuit switch at the same time. 11. Alternative dynamic logic styles. Besides the basic dynamic CMOS and domino logic, there are other dynamic logic styles. NP domino, zipper logic alternates between NMOS and pmos logic blocks. Can be faster than standard domino, but design is more complex. Sense amplifier based logic, SABL uses sense amplifiers to improve noise immunity and speed. 12. When to use dynamic CMOS logic. Dynamic CMOS logic is typically used in the following situations. High performance circuits where speed is critical. Complex logic functions where area can be reduced by using a single NMOS network. Pipelined architectures where the clocking overhead is already present. Memory circuits where high speed and density are required. However, the complexities and challenges of dynamic logic mean that static CMOS is often preferred for simpler, more robust designs. 13. Conclusion. Dynamic CMOS logic provides a powerful alternative to static CMOS, offering potential advantages in speed and area. However, it comes with its own set of challenges and complexities. Careful design, simulation, and layout are essential to ensure correct operation and reliability. While less prevalent than static CMOS in general-purpose logic, dynamic CMOS remains important for high-performance and specialized applications where its advantages outweigh its disadvantages. The charge sharing problem requires careful mitigation through precharging, transistor sizing, or the use of more robust dynamic logic styles like domino. Understanding these trade-offs is crucial for any VLSI designer.